Here we go. No talking. Okay, one more minute. Okay, pass them out. Okay, if C and D vary with constant rate of change, is D proportional to C? Maybe, or no, right? So not necessarily. It might be, but not necessarily. So how would you explain what's in terms of proportionality? Okay? I don't know what you're going to say.
You said change in D is proportional to change in C.
Changes are proportional, right? So D and C aren't proportional. The change in D, you can walk around. The change in D is proportional to the change in C. Okay? So if C is independent and D is dependent, then changes in D are calculated how? That's right. Got to get this down because it's really important for what we're starting to do now, and what we're starting to do now is calculus. Okay, we started talking about accumulation last time. Now we're talking about calculus. Okay, so having this at the ready, knowing this very well, and being on the lookout for it is crucial. So that value of k, how is it computed? K is what?
Change in D over the change in C.
Okay, it's that constant. It's that relative size of changes in D to changes in C that stays the same. Any questions? Okay, so know it. If you're still not getting these questions right in the quizzes, it's time to now. It's time to learn it. Okay, we got to know this. All right. So here it is. Two quantities x and y change together such that if we got constant rate of change. Changes in one quantity are proportional to changes in the other. That's what we said. Question number 1 on the quiz. Every change in y is a multiple of the corresponding change in x. And that multiple is called the constant rate of change. And how do we compute it? It's the relative size of changes in y to changes in x. Every change in y is the same size relative to its corresponding change in x. Okay, so as we're starting to talk about accumulation, this is our key principle that allows us to accumulate a quantity, and this is calculus now. Okay, so this is familiar, right? We've got the marginal tax rate function, and we've got the tax due function. So this is, say, for someone who earns, say, by the end of the year, they've earned $58,000, okay? So their annual income is $58,000. They make that last dollar, say, on December 31st. So we want to talk about symbolically, how can we represent that amount of tax due? The amount of tax due on an income of $58,000, we can think of it 2 different ways. Okay? We can think of it 2 different ways. We can think of it as the total amount of tax that's owed, and that would be like going to the tax table, finding $58,000 and getting the value, right? The value of tax that you owe. Or we can think about it as an accumulation of small amounts as the whole year goes by. Okay? So let's start by how can we represent, given what we've got up here, given our functions and given our visualization of that, how can we represent that total tax due, like as a lump sum, as a total amount of tax? How can we represent it using what we've got? How can we represent that? So what do you got? You've got your tax rate function and the tax function. So how could we represent the tax due on $58,000 as a total amount of tax? Jacob, any idea?
Well, you have to make the tax function similar to the ones you did the other day. You have to,
Like this one?
yeah.
Or we already got it. So I just want to now I want to use it to represent how much tax would be due for $58,000. Yeah. So how do we represent? So how do we have? Nicole?
Well, first we would have to find the tax rate, so.
No. I just want to represent this amount of tax. Just want to represent it. Meaning I want something that I write down that when you look at it, mathematically means the amount of tax due on $58,000.
Tax
Just do tax, whatever the point is.
Right.
Equals,
I never said it was a hard question.
how much
Right.
tax is due.
Right.
That's
Right.
the 58,000.
Yeah. You take
It's a function of the,
right. That's the representation of how much tax you owe for $58,000. I wasn't asking for the value, just a representation of it. Okay. Now, similarly, how can we represent that same amount of tax due as an accumulation of small amounts of tax? How can we represent it as, instead of just end of the year, here's what you owe, as it accumulated over the year? How can we represent it that way?
piecewise function.
We've already got the functions. How can we represent the accumulation of the tax?
You add the previous amount to that one.
What's that?
So you add the previous interval to the.
Okay, remember from Friday, how do things accumulate?
Bit by bit.
Bit by bit. And so if accumulation then will be what kind of operation? If we're accumulating bit by bit. Of addition, right? So what will the first thing that we add be?
Change in Y.
Change in?
X.
Change in Y or change in X?
Oh, it's amount of tax, so it's changes in Y.
He wants change in Y. Stanley, what do you think?
Makes sense.
Okay, and our Y is? So this function, right? Change in tax for the first dollar. So that's the tax we owe on the first dollar. And then what? Plus? Okay. And how many of these are we going to have that we're summing together?
58,000.
Lots, right? Every single dollar. So the last one would be 58,000. So this sum, you see that this sum is the same as what's represented on the left, the total amount you would owe. Okay, and we said these little changes. Are these little changes changes in X or changes in Y? Tell me your name again. Tell me your name. Yeah. Yeah.
Christina.
Christina, changes in X or changes in Y?
Changes in X.
She wants changes in X. Amos, disagree?
Yeah, it's changes in Y.
Why is it changes in Y?
Because it's the tax due, not your taxable income.
Yeah, so our X value is taxable income. Tax due is Y. So these are changes in Y, right? Okay, so this should make sense. Does it make sense? Using function notation, this is like using the table. You know, in March or April, our taxes are due, so we open up the table, we look 58,000, we owe whatever, 12,000 bucks in tax, or whatever it is, okay? This would be looking at that same amount, but the tax on $1 at a time. Okay, so because these are all the same, over and over again, we have a way to represent sums like this. We don't want to write this out because each thing is so similar. So it would help to be able just to write it one time. The only thing that's changing is which dollar we're talking about. So we can just put a variable there. So say I. And so what are we doing? We're summing all these up where I starts with 1, and then I is 2, and then I is 3, all the way up to I being 58,000. Okay, so the symbol for sum is a capital sigma. All right, so what do we say? I is starting at what value? 1, and the last value is? 58,000, okay? So this is, some students look at this and they say, oh, those are scary symbols, okay? No, the point is to make it more convenient. So we don't have to write this out. Why? Because they're all the same. All these are the same, so let's just write it once, and then just indicate how they change each one, and then this capital sigma stands for sum. So we're summing up. Summing up all of these delta y's, where the first one is 1, and then we do 2, and then 3, and then 4, and then 5, all the way up to 58,000. Okay, so this is called summation notation. So this thing in blue right here is exactly the same as this expression right here. They mean exactly the same thing. Okay, and because we're talking about accumulation, this is going to be really important. Summing up lots of little bits. Look, 58,000 little bits summed up. So this notation fits right along with this idea of accumulation, summing up bit by bit by bit. This is a typical bit, right? This is a typical bit, and we're adding together a bunch of them. Does it make sense? Any questions? All right, so let's practice. Can you write that? So starting with 1 plus 2 plus 3 plus 4 up to 100. Can you use summation notation to write it? Give it a shot. So in general, it'll look like this. So you'll have your starting value of I. There's 3 parts to it. The starting value of I, the final value of I, and then the rule on I that gets us these right terms to add together. You see? So we need the starting value of I and the final value of I, and then what rule with I will get us these exact terms to add together. So Andrew Myers in the back, Andrew Myers. What's the starting value of I?
1,
Okay, and what's the final value?
100.
All right, you're on a roll. So what rule of I will get us these terms as we let I change from 1 to 100?
Just I by itself.
He just wants I by itself. Does it work? Does it do it?
Sure does.
Yeah, because so when I is 1, the first I, we want the value to be 1. And then we go on to I equals 2. What's the next thing we want? 2. So we just want I every time. We're just adding together I. You see? As I changes from 1 to 100.
So the difference between this and the previous example is what?
Different. Before we were adding together a bunch of delta y's. Here I'm just adding together integers.
Okay.
It's what I'm adding together is different. Before it was delta y's, right? Little amounts of tax.
Okay.
Now I'm just telling you to add 1 plus 2 plus 3 plus 4. It doesn't really have a meaning, right? Okay, so here's the flip side. Here's the summation notation that says I equals 1 to 90. So you write out what that means, okay? Write out what would that mean. Eric, what do you think?
This just can't see.
Oh, you can't see this?
It's so small.
I know. So it's I equals 1 to 90.
So it's 1 plus 2 until to the 90.
So 1 plus, what's the second one? What's the second one?
2.
Just 2?
2 square and
2
3 square. and
2
4
square. There you go.
Until 90 square.
Yeah, until 90 squared, that's what he said. Make sense? Okay, try again. So I'll write it bigger. It's kind of too small. So I'll write it bigger here. It's I equals 1 to n r sub I delta x. I equals 1 to n r sub I delta x.
What is R in this case? Does it not matter? Just
Yeah, this is just practice. But what might it be? Yeah, we'll talk about that in a second. What might that be?
various rates of change at different points.
Mm-hmm.
Is this going to be where we break them down into like this small point that takes us to that point? Maybe I'm jumping over something.
Yeah, but you got. We're gonna approach it a little differently than that.
Okay. Okay.
But yeah, you got the right idea. Okay. Let's see. Yeah, David.
So it's the sum of varying rates of change in relation to the rate of change of x.
Okay.
That goes. Sorry. The rate of change changes by 1 up until it reaches n.
So what would the first term be?
R1 delta x.
Keep going.
R2 delta x. R3
R3. How many total are there?
Rn delta x.
Okay. Does the rate change by 1 each time? So they're picking up on the fact that this might be these R's might stand for rate of change, and they probably would. Okay.
Rate doesn't change.
Does the rate change by 1 every time? Sharon, what does that mean? 1, 2.
Oh,
Does it mean this rate is 1 greater than that previous rate? Yeah, it just means the next one. We have no idea what these rates are, how they differ, or how they change from rate to rate. It just means the next one. This is the first rate, the second rate, etc., and then the last rate. So we're not really sure what the rates are. Okay, so if each one of these is rate times delta x, then what would each one of these things be?
Y.
A y?
The change in Y.
Change in y, right? That's what we're working on. This would be which change in y?
that's what I'm saying.
The nth change in y, and this one would be the second change in y, right? If we had constant rate of change on each one of these rates, then the change in y would be the rate times the change in x. Okay? So this would be a different way to express what? Summing up lots of little bits of changes in y. Okay, one more. Now this is saying, given this, what's the summation notation? So what's the summation notation for this? Going the other way again now. This, Andrew, what does I start at?
1.
Okay, and what's the final value of I?
Okay.
And then what does each one look like?
X sub I
Okay,
times delta x.
agree with that? Perfect, okay, well done. So, when you see this, don't let this scare you, right? See all these symbols, you're like, oh my gosh, that's really scary. It's just summing up a bunch of these, right? It's just a big addition problem where each thing that we're adding together looks just like that. That's what it is. Okay, so let's just do a quick review of, we're going to work with the rocket basketball again. Okay, so just quickly here, where in this animation should you look to see elapsed time growing? Adelaide, where would you look in this whole thing to see elapsed time growing?
Where it says number of seconds or
X-axis. Agree? Yeah, so you see how the bar is a little bit thicker as it comes across? So that's showing the elapsed time as that bar increases in seconds. Okay? Where should you look to see the basketball's velocity for the current value of elapsed time? Where should you look to see the velocity? Autumn.
on the y-axis of, on the left.
She wants the y-axis of the left graph. Yeah, so this is our rate of change graph, beats per second. Rate of change of distance is velocity, right? Rate of change of distance is velocity. So the y-axis of the left graph is telling us velocity or rate of change. Okay, where should you look to see the basketball's height for the current value of elapsed time? Elizabeth?
The y-axis of the right graph.
Yeah, so this is real nice and easy because we've even showing you the ball here, right? So this is showing the height of the ball at any given time. What does the current value of the basketball's height mean? What does that mean if we say the current value of the height? Marcus?
The height at which you're looking at from the height at which is changing per second. Or the space in between the two lines.
So you're kind of talking more about a change in height. So what does it mean to say the current value of the height? Chelsea?
Is it talking about the velocity at that given time?
It's talking about the velocity. This is current value of the basketball's height. Connor?
Total distance from the ground.
Okay, total distance from the ground. All right, so what does it require that we do? Yeah, it's kind of like we have to stop time in order to think about this. So time is going by, time is always going by, and so as far as we know, this basketball is always going up. So in order to talk about a current value of, say, height, we have to say stop time at 3.9 seconds, and that's the current value of the height. The current value is what it would be if we paused time, okay? Okay, so what does a point on this left-hand graph represent? Perfect. What does that blue point right there represent, Tyler?
Point represents how many feet per second the basketball is traveling at a given time.
He said how many feet per second the ball is traveling at a given time. What do you think?
It would have to be that given time.
What's that?
It would have to be that given time. not
Right.
any given
Yeah,
time.
so it's a specific velocity at a specific time. Yeah, so remember, a point is two pieces of associated information. In this case, number of seconds and speed or velocity or the rate of the ball. Okay, why does the basketball's velocity jump discontinuously? So why does the velocity graph jump discontinuously? Connor?
Instead of incrementing upwards, it increases by a set amount.
Mm-hmm.
The rate of change, that is.
Right.
So it doesn't actually, like, the graph doesn't connect because it doesn't actually, basically, it doesn't go through every one of those individual rates of change up until that jump. I don't know exactly, you know what I'm trying to say? Like, instead of being a continuous graph, I guess it's discontinuous.
Okay, it's discontinuous. Yeah,
Well,
of course.
at different intervals, if it's like half-second intervals, correct?
Yeah.
It's jumping up at a different velocity.
Okay.
So it's not changing gradually, it's jumping up to the next velocity in those time brackets.
Okay. So each half second it jumps to a higher velocity. But what happens within a half second time interval? What kind of velocity is it? Constant rate of change. So that's the key, right? So within those, we got constant rate of change, and then suddenly every half second it jumps up to a higher constant rate of change, right? And so, realistic?
No.
Okay. Yeah. So to shoot a basketball upward so that it maintains a constant speed, and then suddenly a faster speed, and then suddenly a faster speed. It's actually similar to bombs that they used in World War II called buzz bombs. They were rocket powered, and it was similar to this. But to be able to create this and actually like this, it's pretty much impossible. Okay, but this idea is crucial for us in order to be able to calculate accumulation. Okay, so although it's unrealistic, it's essential for us to understand how are we going to accumulate the value of a quantity. Okay. Okay. In what way does the basketball heights accumulate? And how is this reflected in the graphs? In what way does the basketball's height accumulate? Somebody new. DJ, how does the basketball height accumulate? Yes.
With each change of y, like change of y by change of y.
Mm-hmm.
I mean, if you can stop it every 0.1 second,
Okay.
then we would see that it's going to incrementally increase.
Yeah, so he said if we stopped at every 0.1 second, we would see that it would incrementally increase, meaning that it's accumulating bit by bit by bit, little bits at a time. Little bits at a time. A little bit of height, then a little bit of height, then a little bit of height. Okay? That's how the height accumulates, a little bit at a time. Like he said, in 0.1 second increments. The height would change each time 0.1 second went by. Okay? So, how can we symbolically represent the height? So back to this question again. So we've got the height of the ball here at 6 seconds. I want you to represent it. So let's say we've got over here, we have the height function. And over here we have the rate of change of height, which also is our velocity, right? So this is the height function, and this stands for the rate of the height function, the rate of change, or the velocity. So how can you represent this height right here at 6 seconds as a single height and as the accumulation of little changes in height? You should be able to do it. Write it down. You can do it. So I'm not asking you to build any functions. I'm asking you to use these functions to represent the height of the ball at 6 seconds in these two different ways. Stephanie, I'll let you take your pick. You can do either one. You got one of them?
I only have one left.
The left, what do you think it is?
Maybe. I have no idea if that's right.
What do you think?
R sub H6.
R sub H6. Olivia, you agree with that?
Yeah.
Olivia agrees. Talia,
I thought it was H.
she wants H of 6. Daniel, in the back, which one? Or something else?
I was trying to figure out the second one. But
Marcus,
V of 6.
V of 6. What are we representing? Height of the ball at 6 seconds. What's that?
It should be H6.
Christina wants H of 6. Yeah, H of 6. Right? H is the height function. Not asking for the rate. So this is the rate, or the feet per second, or the velocity. We want the height at 6 seconds. Okay? The accumulation of little changes in height. Helios. I want to represent the height of the ball at 6 seconds as an accumulation of little changes in height. Any idea? RH of 6. Josh, what do you think? Agree with that? The accumulation of little changes in height.
Maybe like R,
Hold on.
like R1 or RH of 1 or something?
RH of 1. Okay. Is R height? No, it's rate, right? It's the change of height. It's the rate of change of height. And what do we want? We want little changes in height. Dan?
Would it be H1 plus H2 plus H3?
H1
Oh, it's 6.
plus H2 plus H3. Is that what we want?
Changes.
Yeah, so if a little bit is going to be a little change, right? Okay, and then how many of these will we have? So notice that we've got half-second increments. So how many little changes in height will we add together for half-second increments? 12, right?
So in the summation notation, if you did it that way, it would be 6 on the top, and then your starting I would be 0.5. Or is it still 1?
So the I is just indexing, it's like called an index. So it's just indexing along each term. So what will what's I going to do?
Okay, so it still goes up by 1.
Yeah, it's going to just make it as easy as you there would be different ways to do it, but make it as easy as you can on yourself. Okay, so yeah, h of 6 is the height, but then that also can be thought of as the little change of height in the first half second, plus the little change in height in the second half second, plus the third change in height, all the way up to the 12th change in height. Okay? So we'll put that on. Does it make sense? This is really important. Okay? So this is now, some of you have had calculus before or you've heard something about it. This is kind of the underlying idea of integration. Okay? So this is the first half of the course. We're going to be talking about what's called integration. Integration is accumulating little bits of a quantity to get the total amount. So the value of a quantity, or an amount of change of that quantity, can be calculated. This is what we're talking about. How can it be calculated? What's that? Yeah, by summing up little bits at a time of that quantity as the sum total of many little bits of change, and that's accumulation. So remember, tax due on 58,000. 2 different ways. The value of the tax function at 58,000, or the sum of lots of little changes in tax due. Which of these represents the idea of integration? The left or the right? The right. This is the idea of integration. We're adding up a bunch of little changes in tax to get the total amount due. Okay, the height of the ball is 6 seconds. We said was h of 6, or the sum of many little changes in height. Which one represents integration? Plugging 6 into the h function, or summing up the little changes each half second? This. This is what integration is about. Some of you have had calculus before. You had no idea that this was what integration was about. Okay? To you, it was just a symbol that told you to do some procedure, right? It was just a symbol that there was a procedure. This is what the underlying idea is. Accumulation of little bits of a quantity to get the total amount. Okay, so just quickly. a delta tax or a delta H? Is that a delta Y or a delta X? Yeah, these are like delta Ys. Okay, so this is just a little preview here. Do we have constant rate of change for each little change in Y? We have constant rate of change. What did our left graphs look like? Constant rates of change, right? And if we have constant rate of change, how do we calculate delta Y? K times delta X. K times delta X. So that's why this thing was so important. Because when it comes to accumulation, what we're doing is we're summing up a bunch of little changes in Y that are all at constant rate of change. And if they're all at constant rate of change, then each one of those little bits can be calculated this way, by the rate times the change in X. See how it's all coming together. Everything we've done so far is important. It's all tied together. Okay, so what would it look like if now we let time advance here and we graph the height as a function of time? So talk to the person next to you. If we let now time increase on this axis and we keep the height of the ball above the current value of the time, we're going to get a graph. So exactly what will that graph be like? So talk to the person next to you. See what you think. Okay, so I have a question. Is it a curve? Yes or no? Is it a curve? Starts off as a curve. Adonijah, you're...
It can't be a curve because it's a discontinuous graph. And so the slope increases not gradually on that graph, but rather it's got a constant rate of change and then suddenly it changes to the next rate of change.
You like what he said? No? You changing your mind? He's saying there's a constant rate of change and then the slope changes abruptly when we hit the next constant rate of change. So it sure looks like a curve, right? But is it? Can you see? You can barely see it. You see that right there? And right there? And then right there? And then right there? Okay, so this is not a curve. And we know that it's not a curve because we built, what kind of function is this? Piecewise linear. We've been working on these for a week now. Piecewise linear functions based on constant rates that abruptly change, right? Constant rates that abruptly change mean a piecewise linear graph. So let's go back here. Okay, so we've got here's the situation. And we've got all these different rates of change, which we're calling our different velocities, right? So take a look at the fifth velocity, which starts at 2 seconds. Starts right here. And in the next half second, I can represent the next half second like this. Okay, that's half a second right there. How can we represent it symbolically? So what does that change in x, right? A change in x, okay? And that change in x is half a second. In that change in that half second, there's a corresponding change in y. Is that change in y, over that half second, do we have constant rate of change? Yeah, we have constant rate of change. So, what does the change in y equal if we have constant rate of change for that half second? Tell the person next to you. What does that change in y
What is the change in my y?
equal to? How could you compute that change in y if we have constant rate of change in that half second right there? Jatia. Okay, she said k delta x. Agree? Okay, but what is k?
4.
What are we calling k? Yeah, some people are saying 4. But just generally,
E sub 5.
v5. You're right, it's 4. You're right, it's 4. v5 delta x. You see? So we have that little change. All right? So, next half second. What am I drawing now? What am I drawing now? What does that equal? That change in y? v6 delta x. Next half second. Change in x. Change in y equals v7 delta x. We can keep doing that. So that's v8 delta x, v9 delta x, v10 delta x. What's that little change right there? Change in x, change in y, which equals? That's actually v10. Okay, and then another, we'll just do one more. Change in x, corresponding change in y. Okay, so these little, see, so in between the red dots are showing little bits of change in height. And those little bits of change in height are coming from the rate times the corresponding change in x. So that first one we did, v5 delta x. Then the next one, v6 delta x. Ah, darn it. Oh, you were right, it was 11. I did one more. All right, so that right there, that's that increase in height. That right there, boom. See, do you see how it's just the exact same thing, but just this one's represented vertically, and this is actually represented at the graph, but it's the same little change right there. So, how do we get the accumulated height if we want the accumulated height in the first, what is this, 8 seconds? How do we get the accumulated height in the first 8 seconds? What would we do? Helios.
The summation notation starting from 1 to 8.
Yeah, so we're just going to add all these up, right? Each one of these is a little bit of change of height in each half second. So we're just going to add them all up. And so you want to do summation notation. What will it be? So we got 11 of them. I guess that's the first, is that the first 6 seconds? What is that? Yeah, that'd be the first, or 5.5? Yeah, so starting at I equals 1 to 11, and then we're adding all those up. Each one of those is like a delta. Each one of these is a delta H, or a delta Y.
G11 and what does that represent?
What's that?
The G sub 11, what does that represent?
Okay, what does V11 represent? Is that what you mean? Or no, this. Oh yeah, so distance like D, like vertical distance for 11 time intervals. Yep. over all 11 time intervals, right? Because it's the whole sum. Okay. So the homework, so whether you think it's been easy so far or hard so far or somewhere in between, it's going to start to get harder, okay? All these things we really need to understand really well, but now we're going to really get into the nuts and bolts of integration. So it's going to get harder. So your homework for Wednesday is kind of 2 parts, and the second part, you're going to have to kind of read on your own a little bit, kind of figure some stuff out on your own, okay? And then come ready on Wednesday with your best attention, and we'll attack this thing called integration.
Mark, is our homework posted already?
It's posted, yeah.
I'm about my scarf.
I didn't get to it yet. Sorry. Hopefully today. Yeah, you can send me an email if you want to remind me.
Okay.
Yeah.